Okay, we've looked at having just the single trig function secant or tangent where they're raised to powers. In those cases, you could just use your reduction formulas. Now what I want to look at is what would you do if you had products of secant and tangent. Now the same rules would apply if it had been a cosecant and cotangent product, but I'm just going to go over the tangent and secant products. So what these are based on is the fact that you know two integrals. One of them, the integral of secant squared, is just going to be a tangent of x. And the other one is you know that the integral of secant of x tangent of x is just going to be a secant of x. So if I get those as my integration, then I can finish the problem. So I'm looking for a secant squared and a secant times a tangent. Okay, so I'm starting off and I've got a product here of a tangent to the m power, secant to the n. The first case I'm going to look at is when the n is even. So that means you've got an even power of the secant. Okay, what you're going to do in that case is you're going to split off a secant squared. And I'm going to show you why. You're going to have a tangent to the m, and then you're going to take off a secant squared, so you're going to still have some secants here possibly, unless it is just two of them. You're going to have n minus 2 secants left here, but then you're going to have a secant squared that you broke off. Okay, so this is the secant squared that you're breaking off from the others. Okay, now if that is a du, we're going to think of this as doing a u substitution again, just like we did when we had products of sines and cosines. If that were your du, what would your u need to be? Well, we know that if the derivative is secant squared, then our u needed to be tangent. Okay, so what that means is that if a u substitution is going to work here, I want this entire expression here to be all tangents. Well, that should be easy enough if, remember, n was even. If n was even, then I know that n minus 2 is even. And so I can use my trig identity. I know that tangent squared of x plus 1 is secant squared of x. So these are your Pythagorean identities. So I'm going to use this, and I'm going to change those secants over to tangents. Okay, so what that's going to give me then is that this entire side on the left is going to, it can be all rewritten in terms of tangents. So once I do that, then I'm going to let my u be the tangent. My du then is going to follow to be the secant squared of x dx, and then I've got my simple u substitution. Okay, that's case 1. So this is case 1 where the n, the power of the secant, is even. Okay, case 2. Now I'm going to look at the m being odd. Now m is the power on the tangent. Now what I'm going to do is if the m is odd, I'm going to split off a secant times a tangent. Okay, so I'm going to end up with, okay, I'm taking one of the tangents away, so I'm going to have a tangent m minus 1. I'm taking one of the secants away, so I'm going to have a secant of n minus 1. And then I'm going to have just one single secant and tangent. So all I've done is I broke one of these off. Okay, and now I've got secants and tangents on the other one. Okay, now if I break off secant tangent, the intent here is that this would be the du. If that's my du, my u had to be just the secant. Okay, so I'm going to do a u substitution. So now that means that I need this whole other expression here. This part right here needs to be all secants. Well, let's see, I started off with my m being odd. So that means this m minus 1 here is going to be even. As long as that power of tangent is even, I'm going to be able to use this same Pythagorean identity to switch it over to secants. And then that's going to allow me then to make this entire expression all secants, and then I'll be able to do my U substitution. Okay? So both of these cases are relying on U substitutions, and it's a matter of, can I break off a secant squared here or a secant tangent here to be my du? Okay? And it's based on whether the power of the secant was even or the power of the tangent was odd. Now, let's say that neither of those is true. If neither of those is true, that means that the m is even and the n is odd. And in that case, what we're going to do is we're going to take all the even powers of the tangent, because this was the tangent one. We're going to take the even power of tangents and switch them all over to secants. Rewrite the even powers of tangent to be secants. Then we're going to just get a big power of secant, and we're going to be using our reduction formulas there. Okay, so now let's work a few of these. I don't tend to pay attention to, let's see, if this one's even, this one's odd. I tend to look at it and just try to see, can I do a U substitution? What I would do first is I'm going to see, can I break off either a tangent secant, and then if I break off a tangent secant for my du, can I get everything else to be in terms of secants? Or if I break off a secant squared of x, and that would be my du, then I need everything else to be tangents. So that's the two forms that I'm looking for. Okay, and I know I can change even powers of secants to tangents and tangents to secants. Okay, so first thing I'm going to do here, I tend to like to break off my even power of secants first, because that's the one I learned first maybe. So I'm going to do that. I'm going to break off an even power of secant and then just see, can I get everything else to be in terms of tangents? Okay, so what I'm going to have then is I'm going to have the tangent cubed. The secant squared, I'm going to write as secant squared x times another secant squared. And now I'm setting it up here where this will be my du. So if that's my du, my u had to be tangent. Okay, so now that means everything else, everything here needs to be in terms of tangents. Okay, can I write that all in terms of tangents? Well, the tangent cube's not a problem. The secant squared's not a problem. So we can get that to be entirely secants. So, or tangents. So I'm going to leave this as a tangent cubed x. I'm changing the secant squared to be tangent squared plus 1, or 1 plus tangent squared. And now I've got that secant squared that I broke off. Okay, so now I'm ready for my u substitution. U is the tangent of x, so the du is the secant squared. So this is just going to be the integral of u cubed times 1 plus u squared times the du. Okay, so now we just have a simple polynomial. So I'm going to distribute it out since there's no product rule. That's u to the third plus u to the fifth du, which integrates then to be u to the fourth over 4 plus u to the sixth over 6 plus c, which is equal to, going back to my original variable, tangent to the fourth x over 4 plus tangent to the sixth x over 6. And that's your answer. Now this same problem, could I have broken, the n was even, the one for the secant, but also the power of the tangent was odd. So I could have also broken off a tangent times a secant. So let's see what that would look like. I'm going to break off one tangent times a secant. And so what's going to be left then is I'm going to have a tangent squared of x, and then I'm going to have a secant cubed of x. But this one's the key. This is your du. If that's my du, that means my u is going to have to be secant. Okay, so that means everything else here needs to be secants. Okay, well that's easy enough because I can change the tangent squared over. So this is just going to be secant squared of x minus 1 times the secant cubed of x, and then I've got my tangent secant. Okay, So now my u substitution, here's my du. My u is the secant, so this becomes the integral of u squared minus 1 times u cubed du, which distributing is u to the 5th minus u to the 3rd du, which is u to the 6th over 6 minus u to the 4th over 4 plus the c, which then goes back to secant to the 6th minus secant to the 4th plus the c. Now notice the answers don't look alike, but if you wanted to make them look alike, this is equivalent to this one, but you'd have to use several applications of the Pythagorean identity to show that they were actually the same. Okay, so now let's look at the next one. Now I've got an even power of the tangent and an odd power of the secant. Okay, two things I would look at. I can't break off a secant squared. That's pretty clear. Okay, so this one I can't break off secant squared. I could break off a secant tangent to be my du, so I'm just always trying to break off one or the other and switch the other stuff to the whatever the u needs to be. So now this will be tangent, one single tangent, and then my tangent secant here. And this part, if this is my du, my u needs to be in terms of secants. Well, that's not going to work because I'm not going to be changing a tangent, a single power of tangent, to a secant. So I can't do that, and I couldn't break off the secant squared. But what I can do is I can rewrite this whole thing in terms of secants. So I don't pay so much attention to whether the n's even or n's odd or m's even or odd. I just look at, can I break off a secant squared? Can I break off a secant tangent? And then based on those du's, what would the u need to be, and can I switch it over? So this one, we're switching everything over to secants. So I'm just going to turn this tangent squared into secant squared of x minus 1. I've got a secant of x. So now I've got an integral of secant cubed x minus an integral of secant x, which the integral of secant cubed we just finished. Okay, or using the power reduction formula, I know that that's going to be a secant x tangent of x over 2 plus 1/2 the integral of a secant, which was, let's see, well, I've got 1/2 integral of a secant, but then I also have right here, I have a minus an integral of a secant. Actually, I don't have to do it twice. So I've got, these two would combine to be just minus 1/2 of the integral of secant. Okay. So now, this was done through the power, the reduction formula. And then this one just is out the side. Okay, so now I've got 1/2 of secant times a tangent. Okay, and then this, again, this integral here would just be, we have secant x tangent x minus 1/2, and we know the integral of secant is natural log of secant plus tangent and plus my c. Okay, so these were your formulas, your rules on how to handle when you have even or odd powers.